So now what about when we have stoichiometry? So this gets to our relative reaction rates, okay? And I'm just going to draw up a simple generic example to talk about relative rates, and then I'll give you a real example, okay? So suppose we have the reaction A plus 2B goes to 3C plus D, okay? So if I were to follow through on that simple definition, right, it's 1 over the stoichiometric coefficient times dJ dt, all right? Then now what I can say is, if I start with D, okay, so D is just going to be d dt, okay? And it's 1 over 1 because there was a stoichiometric coefficient of 1 there. I'm not going to include the 1 over 1. So it's just dt, okay? I think that's what I said. So now in terms of C, I'm just going to write dc dt. And if I just follow this, right, 1 over the stoichiometric coefficient, it's just 1 over 3, okay? And then now in terms of B, we know that that stoichiometric coefficient is -2. So that means this is -1/2 dB dt, okay? And then A is just going to be -1 over 1, so I'll just say negative dA dt. And now these are all of the relative rates. These rates will all be equal now that I've considered the stoichiometric coefficients, okay? But if I don't consider the stoichiometric coefficients and I want to know, well, how will the rate of D depend on the rate of C, okay? Well, we would expect to see that C is produced 3 times more than D for any one given unit of time, okay? Or for example, 2 of B is consumed for every 1 of A. And so now if I'm making all these rates relative to each other, that's why it's 1 over the stoichiometric coefficient, because it puts them all at the same rate, okay? So here's one example. So here's the reaction, and I'm going to do lots of fundamental atmospheric chemistry examples. So we're going to see lots of things involving oxygen, ozone, NOx, so oxides of nitrogen. That's what you get your car smog checked for, is NO and NO2. Okay, so here's one example reaction, okay? And so if I were to look at a time profile, time versus concentration of this reaction, so lowercase t for time, uppercase T for temperature, because temperature is a state function, okay, then I would see the following, all right? So I recognize, so I'm just going to draw the rate of O2, okay? So let's do that in one color so we can see it, all right? So here is O2, okay? So now we recognize, hopefully we recognize, that NO will be consumed twice as fast as O2, okay? Again, if I wanted to set them relative to each other, it would be 1/2 NO equals O2. So that would give me my relative rate, but my absolute rate would actually show me that the slope for NO is twice as steep as it is for O2, okay? So I would actually see a slope. If I picked a point, let's say that point, my slope right there, my rate would be 2 times as steep as my rate for O2 because of that stoichiometry. And then correspondingly, what I would see for the product for NO2, it will have the same rate as NO because of the coefficient of 2, assuming that I can draw those things being equal. But of course, they will be opposite in sign, okay? So that's the manifestation of relative rates versus absolute rates. And of course, if I wanted to make, for this reaction, if I wanted to make all those rates relative to each other, then it would go -1/2 dNO dt equals -dO2 dt, which equals 1/2 d NO2 dt, okay? So for now, it's good to just practice with getting 1 over the stoichiometric coefficient. When we build up the rate laws, we'll see that if, let's say we were interested in NO, and I wanted to figure out how to deal with this 2, as we shall see, what we end up doing is multiplying by -2, right? And that would cancel this 1/2, but whatever's on the other side of the equation gets multiplied by -2. Okay, we're going to see that when we put together a rate law. Okay.